Hello, in this video we're going to talk about the conservation of energy, and this is a really big idea in physics, one of the fundamental ideas in physics, honestly, is this conservation of energy. And so you see here kind of the definition, I guess, but the conservation of energy is the idea that energy can be neither created nor destroyed. It can change forms, right? It can go from one type, we talked about potential and kinetic. That's what we're going to focus on mostly, but, it can go from potential energy into kinetic, and then, you can have kinetic energy and change back into potential. I mean, it can change forms fairly easily, but the total energy is the same. And this is actually a really big statement about our universe, right? Because we see energy all around us, and the idea is that all the energy you see, even not just around us, but when you look out at stars, you see they have light and heat, that they have heat, that's energy. All the energy that you can see is finite. It is a set amount, and you could add up all the energy in the universe and you would get some number, and that would be the total energy for the entire universe, and that will never ever change, no matter what. Now, there's this cool idea called the Big Freeze. It's a way the universe might end, right? And so it's the idea that if there's a set amount of energy in the universe and there can never be more, well, if our universe is expanding, which as evidence seems to suggest, then you have more volume but the same amount of energy. Well, if you look at what you could call the energy density, how much energy is there in a set amount of volume, that's going to decrease as the volume increases, right? Because you have the same amount of energy divided by more space, means it gets colder in the average. And so eventually, if it gets big enough, then if you have some amount of energy divided by this huge, immense number, then that's what's called the Big Freeze. The idea is that it's so cold that the average temperature approaches absolute zero. But anyways, that all comes from the conservation of energy. So energy, period, is always conserved. This is absolutely true. There's no caveats to that. Energy is conserved. But we're going to talk about today a specific type of energy called mechanical energy. So again, you may want to write down this stuff here in this equation. You can pause to do that. But mechanical energy is the sum of the potential and kinetic energy in a system. Right? So mechanical energy is a bit more specific. It's just the potential and the kinetic added together in a system. And you can see that here. The mechanical energy is going to be the potential plus kinetic energy. And so for our purposes, the mechanical energy is going to be conserved. It's a little bit more specific. There are two conditions that have to be true for mechanical energy to be conserved. First of all, the collisions have to be elastic collisions, and secondly, there has to be no friction. All right, as long as those two things are true, then our mechanical energy is going to be conserved. Now, if you remember from a little bit back about elastic collisions is where they bounce off each other, and the reason why it matters, it has to be elastic, is let's say you had two objects that were going to smash together. Okay? You're going to smash these two objects together. If it's elastic, then they just kind of bounce off each other. But if it's inelastic, then they're going to get crumpled up and maybe stick together. In a perfectly inelastic collision, they crumple up and they get stick together. But it's the crumpling up that's important. And you've seen this. Imagine two cars smashing together. That would crumple up the hoods probably, and they're actually built that way on purpose. But what happens is when these get deformed, they produce heat energy. So again, the total energy is going to be conserved, but if some of that energy is given off as heat, right? If these things collide and you have some heat escaping into the air or the surrounding area, or sound energy, that would be another way. So imagine this is two cars, they would be loud if they were to smash together. So anytime you hear that sound or you see that heat, or even if you don't see it, they do get warmer. You can test this for yourself if you have, I don't know, you're probably in the classroom, if you have a rubber band or something, if you can find a rubber band, you can stretch it. If you sit there and stretch a rubber band and try to feel it, it'll get warm the more you stretch it. So basically this turns into heat. And that heat is a loss of mechanical energy. Same thing with friction, really. Friction produces heat. And so you're going to see this come up a lot. If you have heat in a system, that is a loss of mechanical energy. Again, the total energy is going to be absolutely conserved. When these two objects crash together, you can see the heat that comes off, and you could add that up, and you could add up the sound, and you could add up the velocity immediately after. You found that the total energy would still be the same, but the total mechanical energy, which is just specifically the potential and kinetic, would not be. All right, let's look at an example. Calculate the mechanical energy of a 2,000 kilogram car racing at 20 meters per second on a track which is 200 meters above the ground. And I don't know what my calculator is, so I'm going to pause the video and come back in just a moment. Apparently I hid it for myself because it took me like 5 minutes to find that. But anyways, I have my calculator now. Alright, so it says calculate the mechanical energy of a 2,000 kilogram car racing at 20 meters per second on a track which is 200 meters above the ground. Alright, here's my race car. I guess it doesn't say it's a race car, but it's a car that's racing, so it kind of is a race car. There you go. Alright, there's my race car. Alright, and it's going at, its mass is 2,000 kilograms. And it's racing at 20 meters per second. And finally, it's 200 meters above the ground. Alright, so there's all the information we have. Let's try to find the mechanical energy. Mechanical energy is the potential, so the equation is mechanical energy equals potential plus kinetic. Now, we've talked about both potential and kinetic before, so you should have those equations. So it shouldn't freak you out when I write this. Mechanical energy equals mgh plus 1/2 mv squared. In fact, notice here, what do you have that's in both of these terms? You have an m. You could actually rewrite this equation, by the way. You could use this every time you want to. You could say the mechanical energy is m times gh plus 1/2 v squared. Or v squared over 2. I mean, you could use this equation every single time if you wanted to for mechanical energy, and it should work out. But anyways, I mean, however you want to do it, I'll use this form here just so it's not too confusing. But again, these are the same, right? You just pull m out from both terms. Alright, so mgh, so 2,000 times 9.8 times the height, which is 200 meters. Plus 1/2 times 2,000 times v squared, which in this case v is 20 squared. So I can tell immediately it's going to be a lot, right? And these are pretty big numbers. But that's okay. I mean, it should be a lot. There's a lot of energy there. So for this first term, I get 3,920,000 joules plus. For the second term, just 40,000 joules. So you can see here that this the potential energy is actually a lot bigger contributor to the mechanical energy in this case than the kinetic is. That's not always true. It's just for this object, since it was up 200 meters, that's a lot. All right, so you add those together, and you get 3,960,000 joules. And that's mechanical energy. Okay, simple enough, hopefully. Let's look at a more complex problem. So here it says calculate the mechanical energy of a 5 kilogram ball rolling at 2 meters per second at a height of 5 meters above the ground. Alright, we can do that. Simple enough. Again, same equation as last time. This time I'm going to use the alternate form though. Mechanical energy is equal to m times gh plus v squared over 2. So in this case, the mass is 5. Obviously 9.8 times h. Height is 5 plus the velocity is 2. Alright, well, you could do some stuff here, right? 2 squared over 2 is just really 2, right? Because it's 4 divided by 2. Alright, 9.8 times 5 plus 2 times 5. And you should get 255 joules. Again, if you didn't do it this format, you use the other one, mgh plus 1/2 mv squared, you should get the exact same thing. 255 joules either way. They're probably going to do morning announcements in a minute, so if that happens, I will have to pause this, and I don't know if I'll get done before that. So I'll probably have to pause in a second. Alright, so find the velocity of the ball if it rolls down to a height of 2 meters on a frictionless ramp. Okay, now here's the key point. It's frictionless. So what that means is that the total mechanical energy is going to be conserved. Again, I want to emphasize, even if there was friction, the total energy would be conserved. But because it's frictionless, there's no friction, the mechanical energy is conserved, a more specific form. So if we know that the mechanical energy is conserved, then as this thing rolls down to a new height, I mean, we would anticipate it moving faster just from common sense. But let's see what it really does. So let me write the mechanical energy for the bottom of the ramp here. Mechanical energy is going to be okay. I think I'm going to have to pause it for a second. I'll be back in a second. All right, the announcements are finished. So again, I was finding the mechanical energy. So let's write as much as we can for the mechanical energy at the bottom. Right, so I'll use just mgh plus 1/2 mv squared. Okay, the mass is easy enough. It's just going to be 5 kilograms. So we have 5 m times g times the height, which, okay, it rolls down to a height of 2 meters. So a new height is 2 meters plus 1/2 times m, the mass, again, is 5, times v squared, which we don't know. Okay, so this is what I have. I mean, I can simplify if I want to. 5 times 9.8 times 2 should be 98, right? Okay, yeah. So this becomes, mechanical energy is going to be 98 plus 2.5 v squared. But this is all I can't simplify any further. But here's the key. What should the mechanical energy be at the bottom? Well, it doesn't matter. It's still the same. This is the core principle here, the conservation of mechanical energy. That even if it rolls down to a new height, it still has 255 joules of mechanical energy. So instead of writing ME, I'm just going to set this equal to 255. And once you have that, then hey, you should be able to get this pretty easily. It's just a linear, well, I guess a quadratic equation, but it's only one variable there. So you can solve, by isolation of variable. So if I do that, I take 255 minus 98, divide by 2.5, and then take the square root of that answer. Again, hopefully you are comfortable with how I did this, but at the bottom I get the velocity to be 7.92 meters per second. So you see here that it started up at the top, it was rolling at 2 meters per second, okay? So then it rolls down the ramp to a new height that's lower, and all of a sudden the velocity increases. So this matches, the math matches your common sense. It matches what you know to be true. You know that, hey, if I'm on a bicycle and I go down a hill, I'm going to go faster. Well, yes. Why do you go faster? You go faster because at the bottom, there's friction, but essentially the mechanical energy has to be the same. So if you have a decrease in potential, right, there are two pieces here, it's potential and kinetic, potential plus kinetic. Well, in order for the mechanical energy to be the same, if the potential decreases, which is what definitely happens here because it goes from 5 to 2, if the potential is going to decrease, in order for this to stay the same, there has to be an increase in kinetic, and that's exactly what we see. The kinetic energy increases, the velocity increases, and they balance each other out so that the total remains the same, right? So I think I'm going to end the video here, but that's the idea behind the conservation of energy and the conservation of mechanical energy.